Okay, everyone, thanks for joining us for the WRF lecture session overview by Dave Gill. I'm going to record this also, and we'll send you the slides and the recording for later on if some of you couldn't get it. I will introduce Dave. Dave, the stage is yours, so go ahead.
Okay, thank you very much, Ophir. May I ask what the preference would be, Ophir and Gerardo, when there are questions in the chat? Should we answer those right away, or would you prefer to wait till the end of the presentation?
It's up to you. I would say it would be easier if the team, the participant will put their questions in the chat, and maybe we can keep few minutes at the end for a Q&A. And if you plan to address it towards the session, so you can wait with answering. So it's up to you.
Okay, that seems fine. That's what we will do then.
Yeah, I suggest to be flexible.
Okay. Okay, let me share my screen here. Okay, my name is Dave Gill. I'm a software engineer at the National Center for Atmospheric Research that is located in Colorado in the United States. And I would really like to thank the two folks as part of ISC that really helped me out to get this test case available to you, Gerardo and Ophir. So there are really going to be just two simple parts to this presentation. The first is about the WRF model itself. And then the second part, just a few slides, is sort of an overview of what we expect that you are going to provide for us for the competition. So the first piece is, what is the WRF model? So WRF, it's pronounced WRF, it's Weather Research and Forecasting Model. We developed it about 20 years ago, and it's a community model, and a number of you are software engineers. So what this means is that we have a set of source code that is available from GitHub, and it's an open development, so you can get the source code anytime you would like. And actually, that's part of the requirements for conducting the test. There's a specific branch that we have set up for you. The development for the WRF model has been led by the staff at the National Center for Atmospheric Research, and I'll refer to that as NCAR, and then partnerships with universities and other government agencies, and that's in the US and overseas as well. So who uses WRF? We actually have a world domination figure here, and this is as of several months ago. The number of users, different countries, is about 184 different countries, maybe 50,000 different users or so. And you can see that the number of people that are using the model is increasing linearly now, close to about 4,000 people every year. The dominant number of users is coming from the university community for this weather model. So what do you do with this WRF model, this weather research and forecasting model? You can do idealized simulations. This is a supercell types of weather that happens over the Great Plains of the United States, where you have very strong hail and they spawn tornadoes. You can do experimental real-time forecasting. Here what we see is a depiction of different types of precipitation over the United States, whether it is rain in the green, or it's freezing rain, or it's sleet or snow. So these sorts of very subtle changes in temperature and evolutions of physics will cause very different changes in the way that the moisture hits the ground. There are tests that we conduct to look at different physics options. So a convection test. If I turn on one option versus another, what sort of physical fidelity do I receive? There are hurricane simulations. By far, those are the ones that are most fun and easy to see because everybody recognizes what a typhoon or a hurricane looks like. There are uses for the model instead of just a single deterministic simulation where we run the model and we get a single result. A number of people now, because of the availability of large numbers of processors, are trying to start to do ensemble forecasting, where instead of one single simulation, there are suites of tens or hundreds of forecasts that are conducted. And then a statistical analysis of those forecasts are then conducted to give people a probabilistic idea of possible outcomes. The WRF model can also be used for different scales, and we're going to see that later on. This is a regional climate scale, so you can see extending from the middle of the Pacific Ocean all the way to the eastern side of Africa, so a very large domain. And then these areas here that are additional rectangles. So if the outer domain is 36-kilometer resolution, an inner domain, a nest, a subdomain, could be a maybe 12 kilometers, a 3-to-1 ratio. And then inside of that, we could have another nest. This is going to be one of the features that we are going to focus on inside of WRF, this ability to reduce the resolution or increase the resolution, have finer resolution, make the scale smaller. And that increases the fidelity of the model. We can do data assimilation, and instead of producing a forecast, what we can do is we can bring in observations and use those observations to steer the model itself. And there are hundreds of balloon observations. There are, per day, hundreds of thousands of satellite observations. So data assimilation is becoming a very important part of the weather modeling business. The model itself can be used for not only weather, but to do tracer analysis of things in chemistry. For example, here we see ozone forecasting. So the model can be used for research. There are a number of physical and dynamical parameterizations that can be used. So we know what is happening inside of a cloud, but that scale is very small, maybe a thousandth of a millimeter. And we can't really conduct computations inside of a thousandth of a millimeter and then expand that out to the size of a country. So we have to parameterize bulk characteristics of what's going on. We are able to use the WRF model to do specific case studies. So if there was a particular episode or event that happened that had high impact, flooding, a typhoon, a cold outbreak, damage to property, those sorts of cases are very interesting to go back and see why exactly did a global forecast or a local forecast from a national center blow the forecast so badly or make a mistake so badly. What is it that we can fix inside of there? We've seen regional climate studies discussed here. Those are studies that are not just for the next 2 or 3 days, but maybe over the next several months up to a year or so. We can couple the WRF model to a number of external applications: hydrology for flooding, fire for wildland fires. We can couple the model with chemistry to do air quality. Data assimilation is where we try to bring in additional observations to the model to help guide or steer it. And the model is absolutely used in a teaching environment for numerical weather prediction. And NWP, numerical weather prediction, typically what we use the WRF model for is hindcasting, where we know a particular event that has happened and we use the WRF model to see what's it says would be a result of a particular resolution, and that's case that we're going to be conducting. We could do real-time studies, and those are where we say, all right, if I start the model right now, I want to know what the weather is going to be in 12 hours or in 24 hours. So the basic concepts of a numerical weather prediction model, and this is not specific to the WRF model, we basically have a forcing term here, and this forcing term is some sort of tendency. We're going to have a change in some sort of forecast variable: temperature, the wind, the moisture, and this changes over time, and that change in our variable is going to cause some sort of forcing. Or we can say this forcing is going to cause some sort of change in our temperature tendency or our dA tendency. If we take our forecast value of our single variable A, that's really the same as our initial value plus some sort of forcing that we've undertaken over a unit of time. This unit of time we're going to refer to as our time step. Notice that in the WRF model and in a large number of other weather models, what we do is we make a forecast, and this one line here allows us to move the model forward, advance the model forward a single time step. And the single time step is usually very small. In the cases that we are going to be talking about, it's about 10 to 15 seconds. So we make a forecast for 10 to 15 seconds, and then we do another 10 to 15 second forecast, and we integrate the model forward in time until we get to the amount of simulation that we would like to have: 6 hours, 12 hours, 5 days, and we just do it at 5, 10, 15, 20 seconds at a time. So if we are advancing the model simulation with the data that's inside of the model, how do we represent that in the equations that we have? So if we look at a weather map, we have these continuous contours of particular variables. And what we have to do is we're going to grid those onto our model domain. And the WRF model uses grid cells that are very close to squares. So each square has approximately the same amount of area, especially for the innermost domain. This is very true. And then we apply a discrete value to each one of these terms. Even though there is a continuous curve that we are representing, we say in this box here, we are going to assume that the value for this particular temperature throughout the entire box is negative 1.5. Next door, we're going to assume that the value for the temperature within the entire box is 0.2. This discretization allows us to now apply some very simple numerical techniques to solve our partial differential equations. This is a depiction of the entire globe with the usual almost a Mercator sort of projection where there is no North Pole and there is no South Pole. If this is most of the entire globe, usually what people solve with weather models, not global climate models, but with weather models, usually what people want to solve is a limited area region. So for example, here's a map over the United States. A limited area region has a number of advantages, and it has some disadvantages as well. Primarily, the big difference between a global model and a limited area model like WRF is boundary conditions. You can see on a global model that if we are trying to do any sort of horizontal finite differencing at a location, we always have a value to the left and we always have a value to the right. In a limited area model, we are restricted to being inside of this region. And if we need to know information outside, we have to assume that is coming from someplace else. And the someplace else it comes from for us is our external model. So here's another depiction of a global model. And then what we require is a lateral boundary condition. And if you've taken any ordinary differential equations or partial differential equation classes, these lateral boundary conditions are part of the way that you can solve your problem, because if we have these parabolic equations and we are on a lateral boundary, we need to know the horizontal gradient across here so that we can get a time tendency for our value so we can advance our model forward. But we can't generate a horizontal gradient if we have no information that is outside of our domain completely. So here's a nice 3D representation of that if we are in the middle of the domain, it's easy for us to have north and south, east and west boundaries. But once we move to the edge of our limited area domain, all of a sudden our lateral boundary conditions are going to be required to be provided by the global model. This is again, a nice 3D graphic of what our representation for the model would look like. That there is a horizontal discretization that's overlaid on the real topography, on the real atmosphere. And then there is a vertical discretization on these layers that we assume that the model has, if it's like a shoebox, we have a certain number of layers that are stacked inside. So our time tendency is a function of some sort of horizontal gradient for most of our variables. We also can see inside of this figure that if we would like to reduce the resolution entirely internal to the model, this is one of the features that most weather models allow you to do. Higher resolution, smaller features are able to be represented, and this gives you a more realistic representation of what is happening inside of the atmosphere. This is another way of showing the increased resolution. If this is an original domain over Europe, we can see that in our most coarse grid, the Alps are just a smeared area of very broad, elevated topography. But in our most fine grid, so if this is domain 1, and then domain 2, domain 3, and then the highest resolution, domain 4, we can actually see individual peaks and valleys. And the blocking effect of the Alps is a function of not only the elevation, which goes from possibly about 2,000 meters here to over 4,000 meters here, but the local flows are going to be determined by the way that the peaks are oriented and the drainage valleys, etc. Higher resolution gives you better fidelity gives you a much better chance of capturing specific features in your model. This is just to highlight that again, the exact same piece. Looking at the resolution again over the Alps. It's hard to see, but this is, here are the Alps, and this is the northern part of Italy here. As we increase the resolution from 30 kilometers, so each grid cell here is a 30 kilometer by 30 kilometer box. Each grid cell over here is a 10 kilometer by 10 kilometer box. So there are 9 grid cells in each box over here. And then we zoom down once more. This is a 1 kilometer grid cell. It's almost difficult to see the individual pixels, but every grid cell in the 30 kilometer domain would have 900 grid cells of the 1 kilometer domain. So the case that we're going to be looking at, there are 2. We refer to them as the single domain case, and that's because the practice test has just a single domain. It's the course grid only. It's a 3 kilometer resolution, an 18-second time step. We had that DT. So we're going to do 18 seconds at a time. And as we march through our 18 seconds, we're going to get up to a 6-minute simulation. For the 3-domain case, and again, named because it has a total of 3 domains, there's an outer domain, domain number 2, and then an inner domain, is Eastern China. You can see the resolution for the outer domain is 3 kilometers. The innermost domain is 500 meter resolution, 1,000 grid cells by 1,000 grid cells. When you are interested in running the WRF model, it is imperative, it is important, it's required that we do parallelism. Parallelism is where we can have more than one processor try to help us out with getting the simulation done more quickly. And there are 2 ways that we can do parallelism inside of the WRF model. The first way is OpenMP. This is a standard. And it has to be done within a single shared memory processing unit. So in your case, on the machines that we're going to be running on, we would be able to do OpenMP on the largest piece would be within a single node. With MPI, we are able to send and receive messages. MPI stands for Message Passing Interface. And the reason we pass these messages is because we can assume that we do not share any memory. These are processes that we are able to, if we would like to, run outside of a node, and multiple nodes can contribute to the simulation finishing more quickly. A term that we're going to use are these halo regions, and we'll see those in just a bit. For OpenMP, if our entire domain is chopped into 4 pieces, and we would want to cut it into significantly more than that, but 4 is very easy to depict on a PowerPoint presentation. For OpenMP, I've noted that we simply cut these pieces into 4 pieces and they're not separated. So this processor would do all of the computations for this part of the domain. This processor would be responsible for this part of the domain, the 3rd processor here, and the 4th processor. We are able to choose what the aspect ratio of these decomposed domains look like, these shared memory tiles. For example, we could also, if we had 4 shared memory tiles, break the processing into long blocks that are more thin. Parallelism is important. It allows us to complete the job more quickly. Parallelism for distributed memory causes a few problems when we start doing our discretization. So let's assume that we are on a single MPI rank we are on a single MPI process, and we would like to do a 2-point stencil. So our stencil is, here's our left-hand side, and our left-hand side is a function of 2 variables on the right-hand side. And it's basically going to be an I-1 and an I stencil. So we're going to get an average that's going to be valid at this location. For this particular location, ij, I-1 is located here. Both of them are on our MPI process. So our neighboring grid cell is right next door to us. We have no troubles at all doing this computation. As we loop through our indices, we're going to get to an ij that is on the boundary of our MPI process. If we try to do I-1, there is no grid cell here. What that's going to do is it's going to force us to do a communication to the patch that's sitting next door over here. Those communications are extremely slow compared to a floating point operation. So what we do, what every weather model does, is we attach an extra set of rows and columns to our computational domain. And this is read-only information. So we pull information out of here, we just don't write any information back to it. This allows us to do our stencil and generate the data that we would like to without having to have communications for every single grid cell that requires a neighboring grid cell that's in a different MPI patch. We refer to this as our halo region. Some people call these ghost cells. So for MPI, we start off with a single domain, but we need to break it into multiple pieces. So remember that OpenMP was shared memory. We could see neighboring grid cells. So if we needed information from a next door neighbor on a different process, we assume that we know that we have shared memory, and we can just access that. With distributed memory processing, with message passing interfaces, we are not able to assume that we can get at the memory of the next door neighbor by just moving in our own memory space. We have to send messages. Those messages are by allowing us, we use halos to fill up the surrounding regions, and then we fill those up with our communications. So if we look at this particular upper right-hand portion, we can see that we would need halo regions that come from these two associated neighboring patches. Similarly, if we're going to do computations down here, the halos are to the right and above. If we look at this particular patch, the halos are above and to the left. If we look at this particular processor, the halo regions are to the right and below. So we'll focus on this northwest quadrant. So this is a scaled in view. So this is the area over which we're going to do computations. If we need any sort of information along the lateral boundary where we're doing a stencil, we can grab information from the halo region. So here we are overlaying our node, our grid structure. And you can see if we have this location here, anytime that we want to do any finite differencing, our stencil is going to be just fine for a 4-point location. North, south, east, and west are all inside of our distributed memory MPI rank. However, as we get close to the boundaries, there are locations where we are going to require information from our halo region. When you look at the parallelism for WRF, those processor decompositions I mentioned a little bit, you can use default values, but we are going to expect that you are going to want to get performance, and those performances are going to require for you to modify the default decompositions. For example, if we have 32 MPI tasks, The default decomposition would be 4 times 8. We take the two factors that are closest to each other. So for 32, that's 4 times 8. We decompose the y direction with the larger of those two. In this case, that would be 8. And we decompose the x direction. In this case, that would be 4, with the smaller of those. If we have 144 tasks, the two factors that decompose that are closest together would be 12 and 12. It's important that you avoid prime numbers in your decomposition or avoid large prime factors in your decomposition. And that's, in this particular case, the total number of MPI tasks is 160, so you're not really going to be in too much trouble there. Here's an example of what the difference between 70 tasks and 71 tasks would look like. If we have a total of 70 MPI tasks, we take 70, we would get it decomposed by the two closest factors. That would be 10 and 7. 10 is the larger of the two, so that's going to decompose the y direction, or the j direction. 7 is the smaller of the two, so we're going to have 7 decompositions in the x direction, in the I direction. 10 times 7 gives us 70. 71 decompositions is a prime number. So the larger of the two is 71, so we would end up with 71 very skinny rectangles stacked on top of each other. Usually, this is not going to work out very well at all for performance. So because you have 160 processes on your 4 nodes, you're probably not going to have to worry about prime numbers. The maximum number of processors that you're allowed to use is based on the stencil size that we are doing. We saw before that we could do a 4-point stencil. Because of the higher order advection schemes that are going on inside of WRF, we have 5th and 6th order communications, so we would need 3 grid cells on either side of the model. That is a physical limitation on how large or how small the patch is allowed to be. And for performance purposes, if you try to have a patch with less than 10 grid cells on a side, the model will simply just stop and tell you, you're trying to make this too small. It's unlikely this is really what you want to do. For our single domain test case, the 1500 by 1500 grid cell benchmark case, and this is the practice single domain case, we could have 10 grid cells across for each one. We could have 150 decompositions in each direction, north and south. We could have over 22,000 MPI processors. This would be a very poorly performing test case, but you can see, since we are only asking for a maximum of 160 MPI ranks with the test case, that you are in the region where we're going to scale very well. Okay, now the second part of the presentation, just the overview of the competition itself. There are 2 wiki pages that we have, one for the single domain and one for the 3-domain WRF cases. The single domain wiki page takes you through everything that we would like you to do in a very procedure-oriented, step-by-step process. We would like you to run the WRF model, and this is for results. We only care about the 3-domain case. And we care about the timings. That's one of the pieces that is going to tell us how fast did this model run. You're going to give us a report of the timings, and there's information in the wiki page about that. Because this is a forecast forward in time simulation with real data, validating the model results is an important step. It would be difficult for us to try to generate a technique that is available in general to say whether or not this simulation is okay. We have done a large number of tests, and we have manufactured a statistical analysis that allows us to look at your results and look at the original results that we obtained to determine whether or not the results that you are presenting are acceptable. This is all also explained in the wiki page. There are a couple of other items that we would like you to take a look at. The impact of compiler options. So for example, changing optimizations or changing flags that are specific for particular compilers. There are parallelism options. We saw before we can change the aspect ratio of the layout of the decomposed areas, whether they are long, skinny rectangles or narrow, tall rectangles or squares. We are interested in running Profiler on the code also. All of these pieces are described in the wiki page. There are things that you are allowed to modify. If you would like to change which compiler you are using, and there are several available, or which version of the compiler, the particular build options, those are just fine. The mix of OpenMP and MPI is entirely up to you. This is a multiplicative scaling. So if you have a total of 160 processes available on your 4 nodes, you can have 160 MPI processes. You could have, and then the other end of the spectrum would be, you could have 4 MPI processes, that's the smallest number, 1 for each node, and then 40 OpenMP threads within each one of those heavy MPI processes. So there is a large state of testing that is available for you to explore. Different flavors or versions of external libraries are just fine. And what this means, there are message passing libraries that are available. Impitch, Impavich, OpenMPI, any of those would be fine. That's flavors of external libraries or versions of those. If you want to do version 1.2.3 or version 2.3.4, anything that you can get to work for these external libraries, and there are only a couple, are just fine. What you are not allowed to modify is the WRF model source code. And this is a Fortran, primarily a Fortran model. The runtime configuration file is a construct in Fortran that is called a namelist file, and that's described also in the wiki page. There are pieces that you are allowed to change that are described in that wiki page, and those really relate to how you modify and orient the number and the orientation of the MPI and OpenMP processes, the MPI ranks and the OpenMP threads. Just for references, I'm just going to, here's the single domain practice case wiki page and the 3-domain competition case. All right, and that's going to do it. I'm going to open it up for questions now. Ophir and Gerardo, is it easier for you guys to read the questions if they're in the chat, and then I'll answer those, or how do we want to proceed?
There's a single question in the chat at this time.
Okay. Let me
just open the chat. I also posted you another question I got via the email. It's slightly long. And then everyone, if you want, just open your microphone and just ask the question.
Okay, so here's the first question in the chat. What is the format of the input files of WRF? Are they in the netcdf format? We intend to install WRF with pnetcdf support and the format of the input files is important to know. Yes, the WRF data is in netcdf. The files are in compressed netcdf4 format. You can certainly utilize pnetcdf. However, it is not going to be mandatory that you work on any optimization for I/O. The timing results that we are going to be conducting exclude all of the I/O timings and even a little bit of the initialization to get rid of all of the. We only want to look at how fast you can get things to run without any without concerns for how you're going to get the input and output to and from disk as fast as possible. I/O is not part of it, so netcdf or pnetcdf, either of those would be just fine. The important part is that it's a compressed netcdf4, so you would simply have to have a version of pnetcdf that handles that also. pnetcdf, for everybody except for the person who asked the question, stands for parallel netcdf. It allows you to have multiple processes open up a single netcdf file, and then those processes are able to write to that netcdf file synchronously. All right. Question number 2. We learned from the WRF User's Guide that when WRF runs a real case, we first use WPS, which is the WRF preprocessing system, to download some files from a national database and generate some input files for the real program. Then the real program will generate additional files, the WRF boundary file and WRF input file for WRF. We haven't installed WPS, so we haven't gone through the steps of running WPS in real. So have you used WPS in real to generate the necessary files for WRF? So for question number 2, basically the question is, do we have to run WPS? Do we have to run the real program? The answer is no. We have manufactured input and boundary data for you so that you do not have to go through the steps of generating all of the
intermediate.
Yeah, you don't have to generate any of the additional pre-processing files. We are entirely focused on the WRF model generating a very large data set that you will be running tests on with a large number of processors. We are in this just for big performance, and we do not at all want you to be derailed or spend any time on the pre-processing aspects of this.
There are 2 questions on the WebEx chat that came in before near the beginning. I'll read them to you. Can you make retro predictions with this model, that is, find the type of climate or meteorological conditions in the past?
So this is a very, very good question, and it's hopefully you saw that was what I was trying to focus on in the presentation. So there's a lot of technical detail about the actual competition itself in the wiki pages, but this overall presentation was to show you what you can do with this type of software package. The WRF model allows you to generate a prediction, and we can put that in quotes. If your initial starting point is from a week ago, or your initial starting point is 10 years ago, you can do a forecast, you can do a simulation, is probably a better word, for the meteorological conditions at that time. A number of national centers provide data that extend back over 50 years with this initial data, so that you can find these. If you would like to do your favorite forecast from the 1950s, or a particular storm event happened in 1975, or you want to see something that happened in the year 2000. There are initial condition data that allow you to start the model, and then the model doesn't know if it's running a true forecast or if it's running a hindcast. A retro prediction is what you're called. So absolutely, the WRF model is definitely used for these types of simulations. Climate tends to be something that global simulations use. We are much more concerned with regional effects in the meteorological conditions, something that's more referred to as weather as opposed to climate. Would 1D decompositions give better performance because there'd be less communication than 2D decompositions? When we started this is wonderful questions. When we started the WRF development in early 2000, probably most of you were not only weren't in school, some of you weren't even born. The number of processors on a big machine was very small. Maybe except for Gerardo, maybe except for SGI. Everybody had a handful of processors, and that was considered very large. And the way that you could get reasonable performance is by taking a domain and making it look like a checkerboard, and then you sent communications back and forth. There are two different processes going on inside of any numerical weather prediction model, inside of any climate model. And those are horizontal processes and vertical processes. The horizontal processes are things that make a lot of sense to you intuitively. If you have wind blowing around, that's a very horizontal process. If you're standing outside and the sun is shining, you're looking straight up, the sun is shining down on you, there's a cloud above you, it provides shade below you, it rains, it makes the ground underneath you wet, or it snows on you, or there's a downdraft and it cools the grid cell underneath you. So there are horizontal processes and there are vertical processes. We had to choose one where we are going to do our decompositions, and we chose the horizontal processes because the physics has many more if tests, and trying to do a decomposition in the vertical with if tests made performance a real problem. The horizontal decomposition, if you've looked at Navier-Stokes equations, there really aren't any if tests until you start to get close to a lateral boundary condition. The exact same flow happens everywhere. So the 2D decomposition, it turns out, is going to be the thing that is going to give us the performance that we would like to see right now.
Dave, I think that what the question was asking about was that the composition, and not referring to the vertical versus the horizontal, but a 1D decomposition in the horizontal. So in your example, I think the question means, wouldn't it be better to do 1x4 instead of 2x2?
Oh, okay, sure, got it. These are, in English, we say arm waving things because we have no real concrete advice, but we just put our hands up and we say, oh, it's probably this way. The exact purpose for this competition is for you to find, with your particular set of compiler options, with your particular set of libraries, what gives you the best decomposition. There are arguments that you would say it's better if we go in a particular direction versus this direction, but those arguments fall apart once you start measuring data. So the honest answer is, I ran it with just a square decomposition instead of long, thin ones, because I didn't want to tip the hand or hat to say which is probably going to be better. But there will be noticeable performance differences when you start reorienting processes for OpenMP and MPI in different directions. It's very interesting.
Yeah, let me field the next question. It says, if you have generated the input files using WPS and real.exe really for us, could you tell us how did you install WPS? That is, what are the compilers and libraries, and when installing WPS, and what are the values of the environment variables, the MCC and the MFC and the configure WPS? Because we learned from the internet that the compilers used to install WPS should match those used to install WRF. No, that is not true. I don't know who told you that, but the WRF input and WRF boundary files that you are being provided are in netcdf, which is compiler, and that's a file data, a data format that is compiler agnostic. Those files could have been generated with GNU compilers, and they will be readable by PGI, by WRF.exe compiled with either PGI or GNU compilers or Intel compilers. I don't know where you learned from the internet that, but that is not correct.
I have a question to the team. Did anyone try to download the files, and do you have any problems or issues? The input files are available on the wikis link. The links are available there. If you have any issues, let us know.
All right, there's a question, is running WRF on a GPU without modifying the source code acceptable? Yes. However, we have spent quite a bit of time with the WRF model and with GPUs, and this is a CPU-based code. We don't want to discourage anyone from any sort of investigation, but we are telling you ahead of time that is unlikely to be a fruitful direction for you to be spending time.
Yeah. Well, we might mention that NCAR and collaborators have been working on a next generation weather model called MPAS, that has been looking at exploiting GPUs, correct?
That's correct. There are software development in progress that will allow GPU utilization, and we see a noticeable speed up, maybe single-digit speed up versus CPU. But for the WRF model, the focus should basically be spend time on CPU optimization. There's a question, Ophir and Gerardo, about not being able to download some data.
So I will check it. I got this also on the mail, and I will check. The file should be open, so maybe some kind of permission issue. I will check, make sure to that the files can be downloadable. I will continue this on the Slack. So I will update you on the Slack.
But in any case, they're supposed to work first on the one domain case, right?
Yes, they can work on the one domain to practice, but we already give them the 3 domains to practice as well. By the way, the Niagara cluster access should have been sent to your team captains. So if you haven't got that, or if you have any issues to access the University of Toronto cluster, let me know. And on a side, later on today or tomorrow, I will send the NSCC cluster. And we don't ask you to test WRF over there, only on the Niagara cluster. But for other applications, you'll need that. So I will send the team captains the information about the NSCC cluster access. Any additional questions? Okay, so just about on time, I would like to thank Dave Gill for a wonderful presentation that starts very easily and gives a good overview on the WRF and on the competition requirements. And again, continue to, we can continue the discussion on the Slack channel for the competition. We have the details on the website. And if you have any questions, feel free to contact us. I'll try to help with whatever we can. Okay. Okay, so good luck, everyone, and see you on our next overview on Wednesday with GPOW. Okay.
Bye, everybody.
Thanks.
Bye.
Bye.
Thank you, everyone.
Thanks, Ophir. Thanks.
You're welcome.